Hello everyone, I hope all of you are doing well. We will be looking at the idea of position vector and unit vector today. Okay, all right, so position vector. We will first define what is meant by a position vector, and the basic idea is very simple. Position vector enables us to locate the position of one point with respect to another point in Cartesian space. Okay, so enables us to locate the position of one point with reference to another point in the Cartesian space. All right. Let's start off by looking at a hypothetical example. Okay. So first I'm going to draw the Cartesian coordinate frame, which is your typical x, y, and z directions, based on the right-handed rule that we have defined earlier. Okay. So here is the x-axis, the y-axis, and the z-axis. I'm going to mark them in a minute. Okay. So this is the x-axis, the y-axis, the z-axis. I have the unit vectors along these directions as little j, and then I'm going to have little I, and then little k. Okay, now the coordinate frame has an origin, right? And I'm going to call that point as the point O. Okay, so this is the origin. The location of the origin is fairly straightforward. The coordinates of the origin are 0, 0, and then 0. Okay, so O is the origin, and then 0, 0, and 0 are the coordinates of the origin O. Okay, that is straightforward. Now let's say that I have a point P which is situated at some arbitrary distance x, y, and z from the point O. Okay, so let's say that I have that point P which is here somewhere. Okay, so this point is situated here, and it is at an arbitrary distance of x, y, and z from the point O. How do I draw these distances? Here is how I do it. Okay, so I go along this way by a certain distance x, then I go along this way by a certain distance y, and then I go along to the top by a certain distance z. Okay, so this amount or this distance, I'm going to call it as little x. This distance along the y-axis, I'm going to call that by a little length y, some arbitrary length. Okay, and then this I'm going to call as the length z. Okay, which means that the coordinates of point P are x, y, and z. Okay, so I'm going to write the coordinates of point P as x, y, and then z, and I'm going to write this statement down. Okay, so P is some point in space at a distance of x meters or something. Yeah, okay, x meters or x feet or something, x meters from O along the x-axis, y meters along the y-axis, and z meters or z feet, whatever is the unit system that you're using, z meters along the z axis. Okay, and x, y, and z are the coordinates of point P. Okay, so this is the information for point P. Likewise, we had information for the point O as well. Now here is what I'm going to do. I'm going to join the point O and the point B by means of a vector quantity. So let's say that there is a vector quantity that is going from point O and ending at point B. Okay, so let me draw this vector here this way. Okay, so here is that vector quantity. Let me make sure that it's joining the coordinate origin here. Okay, then this vector is called as ROP. Okay, this is vector R OP, and this is the position vector that locates point P with respect to O. Okay, so I'm going to write it down. So ROP is the position vector starting from point O and ending at P, helps locate point P relative to point O. Okay, so this is the meaning of that particular position vector. The important thing is it is starting from the point O, which means that the first subscript is the starting point and it ends at the point P, so the last subscript is the ending point. Okay, so if I write this as R O P, okay, so this is the tail point, tail of vector, and then you will see that this point here is the head of the vector ROP, and that point there previously was the tail of the vector ROP. Okay, and this is the position vector from O to P. Okay, and if you want to go back and look at the figure, you can see that the vector ROP starts at the point O, which is the tail of the vector, and ends at the point P, which is the head of the vector. And by definition, the position vector is given by finding the difference between the coordinates of P and the coordinates of O along the respective coordinate directions. Okay, and by definition, so by definition, okay, ROP can be defined as the following. Mathematically can be defined as the following. ROP is given by the coordinates of the point P minus the coordinates of the point O. Coordinates of the last point P minus the first point O. Okay, and this has to be, of course, accompanied by their respective unit vectors. Okay, along the respective directions, and here is how you do it. Okay, you first look at the point P. The coordinates are x, y, and z. The point O, the coordinates are 0, 0, and 0, which means that ROP is going to be the x coordinate of P minus the x coordinate of O times the unit vector in that direction. The y coordinate of P, y coordinate of O times the unit vector in that direction. The z coordinate of P, z coordinate of O times the unit vector in that particular direction. Okay, and this is obviously going to tell you that, okay, ROP, because it's x minus 0, so that's going to be x in the I direction, y in the j direction, and then z in the k direction. Okay, so once again, the position vector is given by the coordinates of P minus the coordinates of O along the respective directions. So I take the coordinates of P, the coordinates of O, subtract them in the x direction, multiply by the unit vector I. Then in the same in the j direction, same in the k direction. Okay, And I can also find the magnitude of the position vector. So this is the Cartesian form of the position vector. Okay, form of the position vector. I can also find its magnitude. ROP is going to be the sum of the squares to the power 1 by 2. This is the magnitude of the position vector. Okay, and one thing you want to keep in mind is that whenever you write magnitudes, the sum of the squares thing is true only in the Cartesian coordinate system because you have right angles. In some non-Cartesian system, the magnitude cannot be written this way. Okay, so this is only in a Cartesian coordinate frame. So in a Cartesian system only. Okay, this is true for any of the magnitudes of the Cartesian vectors that you have seen previously. Okay, so this is the Cartesian form, and then here is the magnitude. All right, now we define the last thing for this particular concept of the unit vector. Okay, unit vector. This unit vector, I'm going to be defining it along the direction of the vector r of b. So for example, if I need the unit vector along the direction of r of b, here is what I do. Okay, so to find the unit vector along the direction of any vector, you take the Cartesian form of that vector and divide it by its magnitude. That's about it. Okay, so unit vector is the Cartesian form of the vector, original vector, divided by the magnitude of the vector. Okay, which means that if I bring back a couple of things from before, so I'm going to bring my figure from here. Okay, I'm going to bring my figure and maybe reduce its size so as to fit it in the next page. So very quickly I bring that and I put that guy here. Okay, so shrink it in, and then here is what I'm going to do. I'm going to say, okay, hey, can you tell me what the unit vector along the direction of the vector OP is going to be. Okay, so here is what I do. Okay, so let's say that I need the unit vector along the direction of OP, and I'm going to point that out as the following direction. Okay, so that's the direction of ROP, right? I'm just drawing something that is parallel to the direction of ROP, so that is completely fine. Okay, so I'm going to call that as U suffix OP. Okay, so that is UOP. Okay, and you can see that this is the unit vector along ROP. Okay, unit vector typically written as U. Okay, I hope my U makes sense to everybody. Okay, and how do I find this unit vector? It's fairly straightforward, right? Because I already know the following. So since we know ROP is xi, yj, zk, and the magnitude of ROP is x square, y square, z square to the power 1 by 2, then UOP, okay, is equal to the Cartesian form of the vector divided by its magnitude. Okay, this is a foundational principle. Okay, so this is xi, yj, zk divided by square root of x square, y square z square, or if I have to be more careful, here is how I would write it. U O P is going to be xi divided by the square root of x square y square z square well, I can take the I and write it next here. So this is in the I direction. Then I'm going to have something in the j direction. I'm just going to copy this and paste it again. Okay, and I'll change a few of these variables. So this is now going to be y in the j direction, and then I'm going to have in the k direction as well. Okay, so I'm going to be doing it as plus in the k direction, and this is going to be z. This is z, and that's in the k direction, and so this is the entire unit vector. All right, so the foundational principle is that the unit vector is the position vector divided by its magnitude. Okay, and the position vector is given by finding the difference between the coordinates of the last point and the first point. Okay, coordinates of the head point and the coordinates of the tail point. All right, thank you very much, and I'll see you in the next talk. Bye bye.